Good afternoon, everyone. This is Chen from RPI, and my topic today is KCompetitive autoencoder for text. I did this work with my advisor, Dr. Mohammad Zaki, and as you know, traditional machine learning requires a lot of feature engineering, which is difficult and expensive. Representation learning aims to automatically learn good features in an unsupervised manner. Those learned features are usually called as embeddings or representations. We want the learned embeddings to capture some designed properties of the raw import data, and as a result, we can use the learned embeddings to as the input features to our favorite machine learning or data mining models and expect they will work well in relevant downstream tasks. The autoencoder is a class of powerful methods which can be used for representation learning. Autoencoders have been successful in learning meaningful representations from image data, but their performance on textual data has not been widely studied. In this talk, we will focus on applying autoencoders to text. So we will first target the issues of applying autoencoders to text, and then discuss a novel k-competitive autoencoder, which was proposed to solve the issues. So first of all, let's see what is an autoencoder. Well, an autoencoder is a neural network which consists of an encoder and a decoder. Look at this example. Given a document, we first map the text into the bag of words representation. Then the bag of words representation will go through an encoder and be mapped into a low-dimensional embedding space. Then the decoder will try to reconstruct the input vector from the squashed embedding. So the idea here is that we assume a good embedding should summarize the input text well enough that we can reconstruct the whole input from the embedding. Let's take a deeper look at autoencoders for text. So each input document is represented as a log normalized word count vector, where each dimension is represented as follows. Here V is the vocabulary size, and NI is the count of word I in that document. As for a very basic one hidden layer autoencoder, the encoder is simply a linear transformation of the input vector followed by some nonlinearity, and the decoder is another linear transformation of the applied to the embedding space followed by another nonlinearity. And in order to avoid overfitting, we usually set U as W transpose being an instance of weight tying, and the binary cross entropy is used as the loss function. After applying autoencoders to text, we observed that traditional autoencoders had trouble dealing with textual data. Here we show the visualization of the normalized topic word weight matrices of AE and KSAE. AE is the very basic one hidden layer autoencoder we just mentioned, and KSAE stands for k-sparse autoencoder, which explicitly enforces sparsity in the embedding space by only keeping the k highest activities in the feed-forward phase. And here the topic weight matrix is exactly the hidden to input layer weight matrix, because we interpret each hidden neuron as a topic which directly interacts with the vocabulary in the input layer. So we trained both AE and KSAE on the 20 news groups dataset. The vocabulary size is set as 2,000, and the number of topics is set as 20. As you can see from the two pictures, both AE and KSAE failed to learn good features from the corpus. If you view the pictures vertically, you will find that a few very frequent words dominate many topics. For example, in AE, the word year, which appears around 4,000 times in the training set, dominate 8 out of 20 topics. While in KSAE, the word year still dominates 4 topics. And if you view the pictures horizontally, you'll find that the extracted topics are not that distinctive from each other, or we say they are not quite diverse. So here we only show the results of AE and KSAE, but we observed similar results from other variants of autoencoders like denoising autoencoders and contractive autoencoders. So we claim textual data is challenging for autoencoders because of the following facts. Textual data is extremely high-dimensional and sparse. The vocabulary size can be hundreds of thousands, and the average fraction of zero entries in the bag of words vectors can be as high as 98%. And furthermore, textual data typically follows power law word distributions, which means a few very frequent words really dominate the text. Here are some sample topics learned by AE and KSAE. You can see a few very frequent words really dominate the learned topics. Like here, line, subject, organ, right. They are all highly frequent words in the training corpus. So we hypothesize that traditional autoencoders greedily learned trivial features in order to reconstruct every element in the input vector equally, and it seems that they only needed to take care of a few highly frequent words, since those highly frequent words dominate the text. So the question is, how to tackle the challenges? Well, someone might suggest using weighted loss functions because it makes sense to decrease the impact of highly frequent words, but in practice, we found it did not help that very much. Autoencoders still choose to greedily learn the indistinctive patterns, since our goal is to learn these distinctive patterns which can capture different aspects of the input data. We instead choose to force autoencoders to achieve this by bringing competition into the training phase. So, intuitively, one of the best ways to have distinctive or diverse individuals is to let them compete. After competition, there will be winners and losers. Someone might be better at one thing, while someone else might be better at another. So we introduced this idea of competitive learning to autoencoders. Specifically, we force hidden neurons to compete for the right to respond to a subset of the input data. Let's take a deeper look at this. Here is the very basic one hidden layer autoencoder with 10 activation functions in the hidden layer. So in each step of feed-forward, there are positive and negative neurons in the hidden layer. So we claim that both the positive and the negative neurons are equally important because they capture positive and negative patterns of the input text. If we interpret each hidden neuron as a topic, a positive neuron represents the presence of a topic in a document, while a negative neuron represents the absence of a topic in that document. So let's look at positive neurons for now. In this step of feed-forward, we have 3 positive hidden neurons, which are H1, H2, and H3. And we select, for example, the top 1 most competitive neuron as the winner, which is H1 in our case. And the remaining positive neurons, H2 and H3, are loser neurons in this step of feed-forward. And here we define the most competitive neuron as the one which has the largest absolute value of activities. So in short, the way we introduce competition is to let the winner neurons take away the energy of loser neurons, where the energy is defined as the sum of the absolute values of activities for a set of neurons. So in this example, the energy of loser neurons is 0.3, and now we amplify and reallocate the energy of loser neurons among the winners using an alpha amplification connection, which is a post adder in this picture. So the new value of H1, the winner, becomes 0.8 plus 0.3 times A, and the remaining loser neurons are further made inactive in this step of feed-forward. And similarly, H6 is the negative winner, and it incorporates the energy of loser negative neurons, and loser neurons H4 and H5 are made inactive in this feed-off step. So you will see the design. Sorry. You will see the design of this k-competitive autoencoder follows the general philosophy of the Matthew effect. So which says the strong get stronger and the weak get weaker. As a result, each hidden neuron is strong on recognizing specific data patterns, and overall, the model can learn diverse patterns and meaningful representations from the input data. So when we do backpropagation, the gradient will first follow through the winner neurons in the hidden layer, and then the loser neurons via the alpha amplification connections. Note that no gradient will follow directly from the output neurons to the loser neurons, since those loser neurons are made inactive in the feed-forward phase. So we argue that the alpha amplification connection is crucial for Kate. When alpha equals 0, no gradient will follow through loser neurons, and when alpha is larger than 2 over k, we actually boost the gradient signal following through the loser neurons. And here k is the predefined total number of winner neurons, including positive and negative ones. And here is the pseudocode for the KATE algorithm. The only difference between KATE and the basic autoencoder is that we apply a k-competitive layer instead of a normal fully connected layer. And once the k-competitive network has been trained, we simply map the input text into the embedding space, and no competition is required for the encoding step, since the hidden neurons are well trained to be distinctive from each other. And we argue this is one of the superior features of KATE, and we will verify this argument shortly. And we also show the detailed algorithm of the k-competitive layer, and we set a hyperparameter k as the total number of winners, and we select k over 2 positive winners and k over 2 negative winners in each step of feed-forward. So here we show the visualization of the normalized topic word weight matrices of KATE and LDA. As you can see, KATE can learn more diverse patterns than AE and KSAE. In KATE, the word year dominates only 2 topics, which is even better than LDA, in which the word year dominates 3 topics. So in order to quantitatively verify that KATE can learn more distinctive patterns than other autoencoders, we introduce a new metric called mean squared cosine deviation, MSCD, to evaluate how diverse the learned topics are. And this metric basically computes how close the angle between 2 topic vectors is to 90 degrees, since 90 degrees means that 2 topics are orthogonal. A smaller value of MSCD means more distinctive patterns. And we can see that KATE is able to learn much more distinctive patterns than AE, KSAE, and even LDA. And we can also conclude that the alpha amplification connection helps learn more distinctive patterns, considering the fact that KATE with amplifications consistently achieves lower MSCD values than KATE without amplification. And we think it makes sense, since intuitively the alpha amplification connection can control the level of competition, and a higher level of competition leads to more distinctive topics. Here we show the summary of the datasets used in our experiments, including 20 news groups, Loisters, Wiki10+, and movie review data. And we evaluated the quality of learned document representations in terms of several downstream tasks, including classification, regression, multi-label classification, and document retrieval. And our baseline methods include autoencoders, probabilistic, topic models, deep generative models, and word representation models. Here we show the PCA projections of document representations learned by variance models from the 6 main groups in the 20 news groups dataset. As we can observe, neither AE nor KSAE can learn good document representations. On the other hand, Kate successfully clusters related documents in the same group and can easily distinguish the 6 different groups. And in fact, Kate even performs slightly better than LDA in this visualization. And here we show the t-SNE-based visualization of the above document representations, and we can draw a similar conclusion. Here we examine topics learned by variance models from the 20 news groups dataset. As we have already seen, AE and KSAE fail to extract meaningful topics. However, Kate generates competitive topics compared to LDA, and which are distinctive from each other and capture the underlying semantics quite well. In order to evaluate whether Kate can learn semantically meaningful word representations, we check if similar or relevant words are close to each other in the vector space. This table shows the 5 nearest neighbors for some query words in the word representation space learned by AE, KSAE, Kate, and word2vector. We can observe that Kate can learn competitive word representations compared to word2vector in terms of this word similarity task, and neither AE nor KSAE is able to find relevant words given a query word. So here we evaluate the quality of learned document representations from variance models for the purpose of document classification and regression. We train a very simple 2-layer neural network as a classifier or for regression. And the neural network uses the learned document representations as input features and directly maps them to the output classes or values. And as we can see, Kate significantly outperforms all other methods across different tasks and datasets. Here we show the multi-label classification results on Loisters and Wiki10+ datasets. And DocNate works very well in this task. And Kate outperforms KSAE on Loisters and remains competitive on Wiki10+. We also evaluate the variance models for document retrieval. So given a querying document, we fetch the relevant documents based on the cosine similarity between the learned document representations. In this task, VAE performs the best, followed by DocNate and Kate. And you can see all the other autoencoders are not that effective. So finally, we study the effects of variance hyperparameters in Kate that we can play with. And we found the number of topics, K and alpha, are some important hyperparameters that we should tune. And let's try to summarize. Traditional autoencoders have trouble with textual data. Kate is able to extracting distinctive patterns by making hidden neurons compete with each other. And Kate can learn better representations than traditional autoencoders, including AE, DAE, CAE, VAE, and KSAE. I mean, they are all different variants of autoencoders. And Kate outperforms deep generative models, probabilistic topic models, and word representation models in terms of several downstream tasks, such as document classification, regression, and retrieval. And as part of the future work, here are a few things that we would like to do. We have tried applying Kate on image data, but it was not that effective. So we would like to dig it deeper. And also, Kate is one hidden layer neural network. So we would like to see if it can enjoy the benefits of depth, which has been widely observed in the field of deep learning. And also, since bringing competition into neural networks is an interesting topic, and might be helpful for some tasks. So we would like to try other alternatives to bringing computation to neural networks. And thanks for listening. Please feel free to ask any question. Yeah.